Thank you everyone for coming. Today I'm going to talk about performance optimizations for data pipelines. So early this year, Airbyte, I'm going to start my timer, give me a second, forgot about that. So early this year, Airbyte undertook a pretty successful performance project. We 4x'd our performance in about 6 weeks, which was pretty good. So today I want to sort of just walk people through that journey, highlight a bunch of learnings, right? Hopefully you all take away with you, learnings that I too took away myself. And then at the end of the day, my goal is we all build better data pipelines together. Cool. So first, let's start with who am I, why you should listen to me. My name is DAVIN. I'm employee number 5 at Airbyte. It's been a wild ride, one of the early employees. Very, very fun over the last 2.5 years. I came in as the platform architect and engineering lead. So, built a bunch of the platform, the architecture, the infrastructure. Currently, I'm the engineering manager of one of the core platform teams. Before this, I was at LifeRam, pretty much doing the same thing, batch and real-time ingestion and distribution to about 0.5 petabyte a day. And I love afternoon tea, which is why I'm very happy to be in London. I love tea and scones, so if you ever want to talk about data, you know where to find me, you know how to bribe me. Okay, so before we talk about performance, let me explain to you what is Airbyte, why we care about data pipelines. So at Airbyte, our vision is to move the world's data scalably and reliably. To do that, we have built an open source ELT platform, right? In that belief, right? We believe that every company is now a data company. Data is your key asset, and therefore, we built Airbyte. This is just the typical marketing spiel, right? The marketing folks paid for my flight, so I have to say all these. We'll be done soon. Over the past 2.5 years, we have grown a lot of adoption. These numbers are a bit old, but we have 60,000 deployments across open source and cloud, more than 2,500 daily active users. We offer 300 connectors, and in total, close to 1 petabyte synced a month across all of these deployments. Okay, so marketing spiel done. Back to engineering. So last year, we were asking ourselves, what is the best thing we can do, or what is the next most high impact thing we can do to better serve our community and better serve data practitioners? And we went back to this quote, which I love, right? I'm sure you guys all heard of it. It's a general sort of software engineering principle. You want to make it work, you want to make it right, and then you want to make it fast. So from our adoption numbers, we told ourselves, okay, yeah, we've more or less made it work, more or less made it right. We could do better, but it's there. So now, let's take on the task of making it fast. So that sets the context, like the background for us taking on the performance project, right? So as I was writing this talk, I was reflecting on it to myself and just wondering, okay, what would 6 months ago DAVIN like to know about performance optimization? So 2 things really stuck out to me. The first thing was how many times I thought to myself, wow, I can't believe it was that. I can't believe it was X, right? Everything that we did to get us to our performance now, nothing was too clever. Everything was very simple. We're not doing any sort of fancy off-heap memory access. We're not shelling out to native libs compiled on bare metal. None of that. Everything was just good architecture, well-written code, and then slowly and methodically figuring out the bottlenecks. So that's the first thing I want to talk about, right? You can go pretty far with today's modern hardware using very simple approaches. So non-wizard, because I think for me, when I first started doing this, I was thinking to myself, oh man, I gotta use this fancy thing. It's gonna be super complex. No. I tried to put in a lot of wizard puns. That failed. So this talk will just be good, solid data engineering, right? Sorry for you guys who love Harry Potter. I did my best. Second thing that I thought was really interesting that I want to share is how effective our eventual approach, the approach we took to a bit more meta, like identify these bottlenecks and act upon them, was. I say eventual because we actually wasted a bunch of time at the start, about 2 weeks, getting lost, and I'll talk about that as well. But this is one of the points I want to touch upon and maybe share so everyone can hopefully use this approach in your own performance optimization work. Okay, I want to start with the punchline. So these are our results, right? what we're looking at is a graph of connection throughput. A connection is an Airbyte term for configuring a source and destination, and you're connecting them. So basically you're configuring and you're telling Airbyte, I want to move data from A to B, right? A being API databases, B being API databases, whatever, file systems. A connection is comprised of a group of logical groupings that change based on the source. So if the source is a database, that logical grouping is a database table, right? If it's an API, it's an API resource. And we can go from 1 to n number of logical groupings. So you can configure a connection to say this only has one table, or it can have hundreds of tables. It's up to you. But this is basically the basic building block of Airbyte when it comes to moving data. We run thousands of jobs a day. So when we came to this, we were like, okay, this is what we want to make faster. When we started in March, we were at 3.5 megabytes per second, which is frankly a bit embarrassing, but it's okay. You start somewhere. That's how you build a product. You know, incrementally you build it, you become better. Within about 6 weeks, or like a month, we were up to 15 megabytes per second. So this is the performance project that we were talking about. That's roughly a 4.2x increase in about 6 weeks. Obviously, your mileage might vary, right? These numbers depend on your source and destination, as well as what's happening in a cluster. So there's some variance. But we saw results as good as this. And in July, there's a gap here, which I'll talk about as well. Eventually, we put this in production and we saw as high as 18. Again, that varies. Okay, so now I want to talk a bit about the architecture, right? So everyone understands what we're trying to optimize. So this is the architecture of a connection. So pretty simple, right? You have a source. Again, a connection is A to B. You have a source container and a destination container, of course. Source container reads from the source. Destination container writes to the destination. Airbyte is interfaces with containers, all Docker based. We do that because we want to, that's the most sort of generic interface everyone understands and knows how to use, and that really helps, or that makes it easy for people to contribute connectors to us, right? Part of Airbyte's value prop is it's easy to make your own connectors and we can run them. In the middle of this, we have the orchestrator. That's the platform piece. So that's doing everything that's necessary to make the sync successful. Lifecycle, stats, schema validation, basic data filtering and obfuscation. That's all done by the middle piece. And these containers are communicating through standard out, so basically Linux pipes. We all know that Linux pipes via a JSON protocol. So we speak JSON. So this is what we're trying to optimize. All right, so the first 7 minutes is all the context. Now you guys are in the same frame of mind that I was 6 months ago. And this is the question I was asking myself. How do we speed this up? And where do we start? I'm gonna give people a few seconds to think, okay? The right answer for most optimization is, let's break out the profiler, right? That is the common answer. If you ask an engineer, that's what they'll tell you. This is a picture of a silver bullet. Silver bullets don't exist. And this is foreshadowing for how ineffective or how much of a silver bullet the profiler was not when it came to end-to-end sort of data pipeline optimization. Okay, and I'm going to talk more about that. But unfortunately, that's what we did, because that's what you do. Someone says, optimize this, you say, okay, we profile it. So we did that, turned on the profiler, looked at a bunch of profiles, analyzed the data. Two things jumped out. First was JSON deserialization. That took about 30%. I expected. People know JSON is not the most performant. And then logging, about 10%. Okay? So this leads us to the initial solution set that we came to. And this is literally taken from an internal engineering presentation. This seems very reasonable, but that is the problem in itself. And I'll explain why. So we said, JSON is slow, cool, let's parallelize it. Logging is blocking, okay, let's make it less blocking. But the problem is, in the best case, we have 40% improvement. Our base is 3.4. That gives us 4.8. That kind of sucks, right? The best benchmarks publicly available today typically is 5. So at minimum, we know that's what we want to hit. Ideally, we go beyond that, but at minimum. So now this leads us to the other two items in orange. They're in orange because essentially we're saying, okay, our architecture is deficient. Maybe we need to do like a bigger rewrite. Maybe we need to change to a different protocol. Maybe we need to explore a different way of moving data, right? Not streaming, more file-based. And they're in orange because these are big rewrites, that's why it's XL. XL here means extra large. Essentially it means it's a heck lot of work. We know it's a lot of work and that's all we know about the work, right? So that's terrible. And furthermore, the impact of these initiatives are unknown. For big rewrites, you essentially have to do most of the work before you can see the impact, right? So this is the worst fear of any engineer or engineering manager. You have an important deadline. My CEO is sitting right in front row, he's looking at me, he's like, yeah, important deadline. And the only way to achieve that is big rewrites, unknown effort, unknown results. Cool. So I think this leads to lesson one. Obviously these solution set was not what we ended up with. We went with a different path, which I will talk about. But this leads to lesson one, which is be profiler informed, not profiler driven when you do this work. That's because the profiler is like a microscope, gives you a lot of data. It's easy to, and in that data, it's easy to miss the forest for the trees, right? If you are doing this yourself, I would not recommend breaking this out. I will only recommend breaking this out if you have done some work before or your component is sufficiently isolated. So if you're doing end-to-end pipelines with components, sort of upstream and downstream, this is not what I would do. Yeah. And so, thankfully, maybe not thankfully, but thankfully, we're a bit stubborn. And also, a lot of us have worked in this space for a while. So this really didn't gel with our intuition. And we said, okay, something is wrong here. We're kind of going on the wrong path, even though it's been 2 weeks. Let's take a step back and just go back to basics, right? So what actually got us to our eventual set of things we had to do was just drawing architecture diagrams and reading the code. Like I said, this is a very simple, this talk is all about simple ways to do performance optimization. Yeah, so I think this is something I took to heart. Nothing beats systematic insight and a bit of elbow grease, just putting in the hard work when you're thinking about performance. So if you're an engineer, don't be afraid to tell your manager, hey, yeah, just give me a few days, I gotta read the code. Do that. If you're a manager, engineer comes to you, says, I need to read the code, trust them. ChatGPT is not gonna save you here. Gen AI, everyone is throwing those words around. It won't really help. Trust me, we tried. Yep. So that's learning one. Learning two is all about backpressure. So as we went further into the work, right, and when we did more experiments, analyzed the data, what was surprising to me is how noisy and how many sort of like side effects backpressure has when you're thinking about the system behavior. So let's go over what backpressure is and just make sure everyone's on the same page. Backpressure is basically signaling upstream components to slow down or halt data transmission, okay? You want that in a pipeline because you want to regulate data flow. When you're designing these components, you design them to operate within a certain bound for good reason. You have infrastructure requirements, resourcing requirements, code, and you want to keep it within those bounds. So backpressure is a great way to do that. In fact, probably the most effective way to do that. So you want backpressure. Now the problem is, and we had backpressure in the initial architecture, right? The problem was with how we had initially implemented it. So recall, I previously said we have containers, and they talk to each other using Linux pipes, standard out. The nice things about Linux pipes is that they backpressure by default, right? If you don't know, just go and try yourself. You write to a pipe, if no one reads from it, you're not gonna be able to write to it. So we have, by default, backpressure within our system without internal queues, which is nice. I could describe this in 2 minutes, in fact 30 seconds, which I did, which is a sign to me of a good architecture. It's simple, it's clear. However, what this means is that in this architecture, right, records are flowing through one at a time, or single-digit records are flowing through one at a time, because the pipes themselves block, right? So that means components now pull data from upstream only after their data is read, and that data is one record. That means the time taken for one record to travel through the pipeline affects all records, and you have backpressure amplification in a negative way. So you're backpressuring too much, essentially. I gave it a fancy term. You have latency amplification. This is not what you want. You want the performance of each component to be isolated. So the solution to this is pretty simple. Introduce proper queues, right? I think this is too simple architecture. Okay, let's add more details if we need to. And we did that. This caused a different problem. So now that we have queues, our first iteration was a fixed queue. That makes sense, right? Let's again try the most simple thing, see whether it works. And what we started to see was pauses in the pipes, okay? And that was because after a bit of heartache and sort of blood, sweat, tears, we figured out it was because our pipes were not big enough. The intermediate pipes did not saturate throughput. And that means, for example, the orchestrator in BigQuery in this diagram was reading faster than the size of the pipes, the queues, the intermediate queues. And this is a challenge for Airbyte because on Airbyte Cloud, for example, we run thousands of jobs. I think we run 30,000 jobs a day now, hundreds of different sources, and the data volume that's flowing through is very different, right? It's hard to imagine hand-rolling configuration for each source and destination pair. And so this is actually what we saw. We saw like a sawtooth sort of performance diagram, throughput diagram, sorry, where the pipe was alternating between reading and processing. This is not what you want. You want something closer to this, where you have an initial ramp up, and then once you saturate all your queues in between, you have a continuous stream, right? You're essentially off to the races once you start booting everything up. So yeah, the problem here is too small a queue, sawtooth diagram. On the flip side, too large a queue, that's really wasteful, right? You are now allocating memory that's not used, reading data that might not be written, and in our case, that really matters. Every single megabyte counts because, you know, trying to make money, so can't be wasteful. And so the eventual solution, again, keeping in mind that we have all these different source destination combinations that people are all running out at different times, was dynamic queues. So we actually implemented dynamic queues that fill up to a certain percentage. For example, here 50%. And what this queue did was, if I'm below this 50%, for example, I start pulling data from my upstream. If my queue is more than 50%, I know I'm fine, right? General principle here is always have data to process. So what we're trying to do is, I never want to block my downstream, and I always want to give my upstream enough heads up so that when it does pull data, it doesn't stop the entire pipe. So this was something I thought was cool that we ran into and then had to figure out. Okay, so I mentioned that the eventual approach we took to figuring all these out I thought was interesting and I want to share. When we were doing it, during the project, it was not that intentional, right? We sort of organically stumbled into this approach. We're being a bit meta here, but I thought it was interesting, so bear with me. And only on reflection did I give this approach like lofty names like build up and peel off, okay? Sounds fancy, but actually it's very simple. And this is anchored on very well-known sort of agile concepts in development. You have spikes, where essentially you want to do a time box experiment to figure something out. And then what we call developing within your headlights, right? You always want to focus on the next most impactful thing. You don't want to get lost in long-term planning or sort of dreaming about the world. And the metaphor here is, at night you want to drive as fast as you can see. If you drive faster than you can see, you're going to crash. And we don't want that. Again, bear with me. We're going to do definitions. I'll show you how we actually applied this. I think it's interesting. So what we want to do is actually use build up and peel off to bidirectionally search our way towards an optimal implementation. So this is how in 4 weeks, we figured out all our bottlenecks and the implementations. And the insight here is, when it comes to performance, the more complexity, the less performance, right? So on the bottom left, you have one cache read. You're doing one CPU instruction. That is really fast because you're not doing anything else. On the top right, you have Airbyte production. Airbyte production has a bunch of features. We're spinning up a bunch of Docker containers, schema validation, lifecycle management, so on and so forth. It's a lot more complex and thus a lot more slow. And we implemented it not very well, so there's accidental complexity as well. Okay? And so here are some definitions, right? Essentially build up, you want to start with a minimal system. You incrementally add features. And each time you add a feature, you observe the bottlenecks. And really what you're trying to do is build a theoretical model of the performance throughput of your current architecture, given the feature set. On the flip side, you have peel off. You take production code, you systematically remove stuff from it. And you basically strip it down to its essentials. Each time you strip it down, you figure out the performance impact of that removed feature, right? Similarly, if you want to make a car fast, the easiest thing to do is just throw out the back seats. Essentially what we're doing. And these are complementary. You'll see later we bounce between them as we converge onto our most efficient and effective solution for that feature set we want to implement, essentially. Okay, so keep that in mind. We're going to go back to where we left off, where I and a couple of guys, my team, were puzzling. We're saying, okay, it can't be true that we have an architectural limit of 4.8 megabytes per second. So how do we use build up and peel off to figure that out, right? That's the question we're trying to figure out. So okay, simplest thing we can do is, given a Docker container, what is the fastest we can read from Postgres, right? So let's spin up one, wrote a 100-line long proof of concept, figured out, actually, we can read pretty fast. 60 megabytes, that surprised me. I thought it was like 20, but 60, that's pretty good. Cool. So that's still within the 5, that's still higher than the 5 megabytes. So hey, actually the architecture might be fine. What's next, right? What if we add the platform container? How does that affect throughput? Turns out, still pretty fast. Okay, so the architecture is still holding on. What if I add a destination? What do we get? 30 megabytes. So actually, at this point, we have proven the architecture is fine, right? Chaining Docker containers together and reading in that the architecture I described, it's okay. There might be faster ways to doing it, but what we have is decent. And so in that way, you see, we're doing sort of build-ups, right? We're adding the minimal set each time and figuring out the performance impact. So now we've proven this. There's a diff. Our theoretical models say we can hit it. Production is not. So let's do some peel-offs, right? What happens if we stop doing stats? We say you can move data from A to B, but we don't know the number of data you've moved, right? What is the performance impact of that? Turns out it became faster. So we're doing something wrong there. What if you move schema validation? You can move data, no stats, schema might be wrong. Turns out, yeah, obviously it went up faster, right? Because you're doing less introspection of the data. So these two features are something we need. So then we switch back to build up. We say, okay, how do we do this in a performant manner? We go back to our theoretical model, we add it, build it in the most minimal way. Instead of counting all fields, you count one field and you figure out, okay, what is that, right? Does that actually move the needle as much as removing all the stats was? What about schema validation? And you do the same. And so in this way, you're jumping back and forth, bidirectionally searching your way towards optimal implementation. Essentially, this is how we managed to figure out all our bottlenecks in 4 weeks. The key here is you want to be as dirty as possible, throw out all the good software engineering principles, write atrocious code is fine. Always incorporate the latest discovery, and always ask yourself, what's the easiest way to test my next thing? Either adding features or removing features. And this is the eventual sort of change set we landed on, right? 3 PRs, all open source because we're an open source company. You can go look at my code, either praise me or critique me. I welcome feedback. In total, 300-ish lines of code. And you can see the fixes were really simple, right? A bit smarter of deserialization, a bit smarter with variable creation, and then adding 2 threads. That's all we needed to do. And I'm kind of highlighting this because, again, simple things can take you really far, especially with today's modern hardware. Like, hardware today is so fast, very different from 5 years ago. So just keep that in mind as you work on your Docker container, work on your pipelines. Whether you use Docker or not, it's up to you. You don't have to use that. All right. So I promised I'll revisit this sort of gap here, where it took us, let's say, 2 months to actually get this into production. And this was a really interesting one, and it's the last learning for today, which is be aware of your observability costs. So what we eventually figured out was, when we started, we added a whole bunch of tracing and profiling. Again, profiling. We were adding, and what we didn't know is actually custom tracers, right? Create an object for the duration of that method call. When we added these tracers, we had accidentally added them to methods that were called on each record processing. So we had inadvertently, via trying to profile, started creating thousands of objects every second that were impossible to track because they existed for a split second. And we were only able to track this down with the help of Datadog support, where we were badgering them and saying, this doesn't make sense, right? It's so fast without the Datadog agent, and it's so slow with the Datadog agent. Something is wrong here. So I'm not saying don't observe. Observe, because data movement or data infrastructure is now key infrastructure, but be aware of that when you're thinking about performance, right? It can affect it in very unexpected ways. Okay, so my last slide here, what I want to leave everyone away with is some pipeline pearls of wisdom. These were sort of interesting nuggets that I myself didn't realize. And after this work, I'm sort of just incorporating into my mental models and my intuition as I design pipelines in the future with Airbyte, hopefully. But yeah, first one is JDBC streaming is surprisingly fast. We could actually read up to 60 megabytes per second. Just obviously, it's very naive, a select star, just reading data out. But I think that's really fast. Second, JSON serialization is actually quite performant, right? Obviously, this is anecdotal, but anecdotal on a single thread, we're reading up to like 30 megabytes a second. So if performance is a concern, serialization protocol is not really where I would first look. And if you're choosing a serialization protocol because of performance, maybe don't do that. Maybe choose it for other reasons, like tooling existing in your org, developer skill set, and so on and so forth. Third, uploading data is often a bottleneck. We end up having to multi-thread our destination clients. So if you are thinking of adding multi-threading into your pipeline, that's the first place I'll look at. It's most likely placed to sort of benefit you. If you go back, everything is single-threaded except the destination container right now. Backpressure is a double-edged sword. We talked about that. I showed 2 ways in which it was unexpected. All the different implications depend on how you implement backpressure. Just think about it and be aware of it. Lastly, record size matters. So record size thin versus fat. If you have big records versus small records, that actually matters what you're optimizing for. If it's a thin records, you're more optimizing for CPU. Fat records, memory. For us, it doesn't really matter because, again, we run so variable workloads, it's hard for us to predict the average data shape. But if you know your own workloads, that's something that can help you optimize or sort of think about your own pipelines. Cool. Last bit. And so I actually tried to do a quick little demo. Oh, it's still running. Oh, there you go, it succeeded. All right, so before I started this presentation, I kicked off a sync on Airbyte. This is Airbyte Cloud. This is a sync running in cloud. In this time, we moved almost 20 gigabytes of data, 110 million rows in 28 minutes. So I think that's roughly 11, 12, 13 megabytes a second. So not our fastest, but again, there's variance and the result of our performance work. So yeah, that's all I have for today. Thank you. I'm around for questions, and we are at booth 724 if you want to drop by and talk about pipelines. Thank you.